Right, good morning, Year 10. So, last lesson, what we did was we introduced electromagnetic waves. Today, we are going to start to look at some of their properties. But in order to understand their properties, we need to understand sort of the functions of waves and how they actually work very similar to other waves. So, a couple of little things. For the higher tier paper, you need to understand that different substances may absorb, transmit, refract, or reflect electromagnetic waves in ways that vary with wavelength. So what that means is, whereas some substances might absorb radio waves, they might allow radio waves to transmit through them. Okay. A good example is glass. So glass will absorb infrared, which is in your electromagnetic spectrum, but will transmit visible light. That's why we can see through glass, but we can't actually feel any heat directly from it. Okay, so some of the effects, for example, refraction, are due to difference in velocity of the waves in different substances. So you should be able to construct a ray diagram to illustrate the refraction of a wave at the boundary between two different media. I'm going to show you how that works in a moment. And then you should be able to use wavefront diagrams to explain refraction in terms of change of speed that happens when a wave travels from one medium to a different medium. Okay, quite a lot there. So the first thing I'd like to do is pause the video and draw a beam of light hitting the different surfaces below. Now, you should be familiar with this. Remember, light is part of the electromagnetic spectrum, like radio waves, infrared, gamma, X-rays. So in that respect, they all work in much the same way. So label and explain what happens. So pause the video and do that now, please. Okay, welcome back. So you should have had something that looked a bit like this. So what happened is our beams of light come in. We know they're coming in because I've drawn the arrows onto it. They hit the reflective surface and they bounce away. Now, what they do is, because all of these, this surface is flat like a mirror, they all bounce or reflect away at a predictable angle, okay? And we call this specular reflection. So if you couldn't remember that, okay, you might want to add this in, specular reflection, okay? And that's what happens when we get a mirrored surface, okay? Now, on, say, a wall or piece of paper or something that doesn't reflect, we still see it by reflected light, but it doesn't reflect like a mirror. The beams of light come in, but because under the microscope the surface is bumpy, the beams of light reflect in all different directions. You see it comes in, that one goes this way, this one comes in slightly different angle, goes off that way, this one comes in at a tight angle, goes off that way. Now, we've got our normal drawn in because it's still bouncing off. So we still draw it at 90 degrees to the reflective surface, and the reflective surface is there. This time it's at a bit of an angle, so it's there. Okay, but we still draw in our normal to show that it follows the same rules. The beam of light comes in and reflects off at the same angle. So the angle of incidence equals the angle of reflection. Okay, it's just because this surface is bumpy, it makes the light scatter. And so we call this diffuse reflection. Okay, maybe just put a brief explanation of what that is now. That'll only take you a couple of minutes. Okay, pause the video again, do that now. Okay, welcome back. So, all of you, by the end of this lesson, should be able to draw a ray diagram for refraction and reflection. Reflection we've pretty much done. Most of you will be able to explain how refraction occurs in terms of wave speed, and a few will be able to describe what happens to frequency and wavelength during refraction and demonstrate this with equations. That might be more next lesson. Right, so this is the practical that you would have done, and you've done a similar version to this in Year 8. Essentially what you were doing was going to shine a beam of light through a glass block, and I'm going to explain to you what you would have seen, and then you're going to draw up something like this. This is actually one of your required practicals and does appear in I'm trying to find which page it is. Yeah, it is on page 77 in your revision guide, so it is worth making sure that you do understand this. Okay, right, so firstly, As you shine a beam of light through a glass block, I want you to observe closely what happens. So hopefully you all saw that, and there, it slows down as it goes into the glass block. And then if you change the angle of the glass block, you get this bending effect. Now, why does that happen? Okay, so let's talk about why that happens. So to understand what happens with the beam of light, remember, light can be transmitted through air, but it can also be transmitted through glass. Okay, so light travels through both. Okay, but glass and air are not the same thing. Glass is far, far denser. So when the beam of light hits the glass block, it slows down. Now, the reason it doesn't bend when it goes in along the normal at a right angle is because the whole beam of light, if I just quickly wind that back, the whole beam of light, the whole wavefront, hits the refractive surface, the glass block, at the same time. So the whole beam of light slows down together. There it goes. So because glass is denser, it basically, light finds it slightly more difficult to get through. Now, when light goes at an angle, we get this bending effect, this refraction. Now, why does this happen? Okay, so a couple of key things here that you need to do. Let's zoom in and see what happens. So, coming in, we've got the top of the beam of light and the bottom of the beam of light. Now, look at what happens. Just pause it. The top of the beam, oops, just rewind that very quickly. The top of the beam has hit the glass, but of course the bottom of the beam is still in the air, still got a little way to go. So remember, glass slows it down because it's more dense. So this part of the beam has slowed down, but this part is still traveling fast. And so what happens is, because that's slow and that part's fast, it kind of skews round like that. See, that's still going fast and creates this bending effect, what we call refraction. Okay, and there it goes. I'll just quickly fast forward that. Now, when light goes from the glass back to the air, the exact opposite happens. It goes back to its original path. And if we just quickly have a look, this is the experiment you would have done. So, our beam of light comes in, and this is what you'll need to draw in a moment. So firstly, we have our normal. So just like on a reflective surface, we'd have a normal drawn at 90 degrees to the refractive surface. So this is our refractive surface here. Here comes our beam of light. It hits the glass block and it refracts. There it goes. And you can see it's going slower because glass is more dense, it's more difficult to get through. And then when it gets back to the air, it goes back to it refracts in the other direction. It basically goes back to its normal path. Okay, now a couple of little things about this, just going to add here. You can add a normal there because there's another refraction there. One thing you might have noticed, how would we describe which way the light bends? Well, if the light followed its original path, it would go like that, but it doesn't. It kind of bends inwards towards the normal. And that's how you would describe how it bends. Okay, so when light goes into a medium which is more dense, like glass, it refracts towards the normal. When it goes to a medium which is less dense, say from glass into air, see here it'd be following its path down that way, but it doesn't, it bends away from the normal. Okay, so that is how you need to describe it. So just going back, what I'd like to do is pause the video, and I'd like to draw your own version now of what happened with a brief explanation. So let's think about the key vocabulary you need to use. You need to talk about fraction, density. So the air and the glass have different densities. How does that affect it? You need to talk about the normal. Okay, so the normal is just, remember, an imaginary made-up line to help us work out the angles. Okay. And you talk about the speed, how the speed changes. Speed of light changes ever so slightly as it goes into a more dense medium. Okay, and then I'm going to show you just one more thing when you've done that. So pause the video now and come up with 2, 3, 4 sentences to describe how what happens to the beam of light as it enters the glass block. Okay, so do that now, please. Okay, so welcome back. Now, there was one other thing I was hoping you would notice, is that the angle of incidence is quite big. You can see there's quite a big angle between the incident beam and the normal, but the angle of refraction is less. So when light goes into a medium which is more dense, the angle of incidence is more than the angle of refraction. However, when it goes the other way, the exact opposite is true. Okay, so when it goes from, say, glass back into air, the angle of incidence is less than the angle of refraction. Okay, right, so can everyone just make sure they've added that in as a footnote, please? Okay, welcome back, year 10. So you hopefully now have understanding of refraction. So all waves can refract and reflect. So we think of light waves as reflecting off a mirror, but also, for example, radio waves will reflect off a mirror exactly the same way as I showed you, as will infrared. X-rays will reflect off a mirror. So if you think about something about how light reflects, our bodies give off infrared radiation. So our bodies give off this kind of radiation here in this sort of wavelength. Now, think about why you might wrap yourself in a foil blanket if you're cold. Okay, because it has exactly the same property as light. It will reflect the infrared radiation back onto your body and keep you warm. Okay, so this kind of electromagnetic radiation, they'll all do the same things, but obviously the differences in the wavelength and frequency do give rise to certain other different properties. I'm going to explain to you about those in a second. But how do the properties of the waves determine what they can be used for? So you've got really long wavelengths here, used for things like radio and TV. Smaller wavelengths, microwaves, used here, and then we've got X-rays at the other end of the spectrum used to see inside things. Okay, so I'm going to explain to you why we use certain things for certain properties. Okay. Okay, so for example, the reason we use long wave to transmit TV and radio signals is because if we were to use short waves like this, waves that have a high frequency and a short wavelength are unable to refract around objects. So basically, the shorter the wavelength, the less it will refract. So basically, change direction. Okay. Also, it won't diffract, which is another thing that we'll get to in a few lessons' time. So what happens is this. So as you can see, what happens there is, because it only refracts a little bit, or diffracts, sorry, I should say, around the object, in this case, say a hill between the transmitter and the house, the signal won't go to the house. So what we do is this. We use long wave radio waves. Okay, we use long waves in order to transmit TV and radio signals. Okay, it's not shown very clearly here, but what happens is longer wavelengths are able to diffract around objects. Basically, the longer the wavelength, the more it can bend around an object, say, for example, a hill. So that's why we use long waves to transmit TV and radio signals, to transmit them around certain objects. Okay, we're going to talk a bit more about that in a minute. So your first task is try and list the types of electromagnetic wave and some of the typical examples that they can be used for. Okay, so once again, pause the video and do that now, please. Okay, now the answers to this can be found from page 78 through to page 80, okay, in your revision guide. So it might be worth having a look. But radio waves, they're used for television and radio, also things like Bluetooth,
You do need to know the difference between what we call shortwave radio signals and long-wave radio signals and why we use them. I'll go through that a bit more in a minute. Microwaves used for cooking food. I'll explain how that works in just a second. Infrared. Now, infrared we feel as heat. So anything which is giving off a lot of heat will be giving off a lot of infrared radiation. So, for example, the reason heat-sensitive cameras work is because our bodies give off heat. So what happens is the cameras pick up that wavelength of radiation. That's why they're able to see it. So it looks like humans are glowing on night vision cameras. Visible light, obviously, we use visible light in our eyes. Used for optic fiber communications. Again, shorter wavelength means you can pack more information in. Ultraviolet, energy efficient lamps, things like sun tanning, and then the highest energy, X-rays and gamma rays used for medical imaging and treatments. Okay, so if you didn't get those, that's a quick summary. So it's definitely worth getting those down. So just quickly pause the video and get that in, please. Okay, welcome back. So there are two diagrams you're going to need to do in a moment, and this is the first one. If you don't get this right away, this is on page 78 in your physics revision guide at the top, and explains how radio waves are made by oscillating charges. So I'll simply just talk you through it. So if, say, for example, you're watching a concert, or there's a concert going on around the world, somewhere in the world, how is it that you're able to, say, listen to that live on a radio? So there's the radio speaker. How is that even possible? So there's our singer. She's singing, and what will happen is she'll sing with a certain frequency in her voice. Now, the microphone is a transducer, okay? It has little crystals, and what happens is it changes sound waves, so compression waves, into an electrical signal of the same frequency, okay? An alternating current. So basically, as her voice is going like, oh, she's holding her note, what's happening is you're creating an alternating electrical current, or an alternating electrical current here in the wire of the same frequency. Okay, so that alternating current will go up the wire, and there's our frequency. It's the same as her voice. Now what happens is it goes up to the transmitter. Now in the transmitter, there are atoms, and what happens is the electrons in those atoms oscillate, and as they do, they basically emit electromagnetic waves. In a nutshell, quite simply, the electrons jump up from one orbit, and then they instantly lose their energy and fall back down. Okay, so the electrons go basically up, down, up, down, up, down. Every time they go up, it's because they're gaining energy, and then when they lose energy, they drop back down and they give out that energy as radio waves. And as you might have guessed, these waves have the same frequency as our electrical signal and also as the singer. So they can travel now out there as waves of electromagnetic radiation. Now, what will happen is our receiver or our area will pick up these radio waves, and that will cause the electrons to oscillate up and down. They absorb the energy from these radio waves, and the electrons go up, but then they fall back down as they give that energy out. And so they start to oscillate with the same frequency. And there it is. And then that can be created into an an alternating current, an electric signal, which can then go to a speaker and pump out those frequencies. Okay, so it's a little bit tricky to explain, but if you go to page 78, I'll just read it out to you now. Electromagnetic waves are made up of oscillating electric and magnetic fields. Okay, that you know. Alternating currents are made from oscillating charges. As the charges oscillate, they produce an oscillating electric and magnetic field, i.e. electromagnetic waves. So as the electrons oscillate, they produce electromagnetic waves. There it is. The frequency of the wave produced will be equal to the frequency of the alternating current. So whatever that frequency is, it'll be the same frequency there. When the transmitted radio waves reach a receiver, over here, the radio waves are absorbed. The energy carried by the waves is transferred to the electrons in the receiver, The energy causes these electrons to oscillate, and if the receiver is part of a complete electrical circuit, it generates an alternating current, which we can go down to the speaker, and it can be heard. Okay, so that is a step-by-step. That's on page 78 in your revision guide. So can you just pause and have a version of this in your book? Now, it doesn't need to be quite as complex as this. Okay, there's actually a simpler diagram, page 78. So can you please draw that in with the 8-point, the 8 points about how you actually do this. Okay, so once again, pause the video and do that now, please. Okay, welcome back. Now you'll need this diagram in your book in a moment. So this is showing how radio waves are used to communicate. And again, this is on page 78 in your book, but you will need this diagram. So, firstly, long waves. Now, long waves, remember, have a long frequency, a long wavelength, so a low frequency. Now, this means they can diffract, so bend around the surface of the Earth. And you can send these quite long ways, okay? So they can bend to get maybe halfway around a continent with these. So they can be transmitted quite long ways, okay? Because they can diffract around hills and they can refract around the Earth's surface, that kind of thing. So it makes it possible to receive these if you have line of sight. That means if you can see where you're sort of sending the signal, you can use long wave radio. However, there are a few drawbacks. Okay, it won't bend around the surface of the Earth. So again, you've got a certain range with that. Okay, so can you just draw something like this in, showing that long wave radio waves, they have lengths of about between 1 and 10 kilometers, and they can be used transmit signals around halfway around the world because they can diffract around surfaces, things like that. Okay. Okay, welcome back. Now, shortwave radio waves, so these ones have between 10 and 100 meters long. These ones have a bit more energy, okay? But because they have a longer wavelength, they don't bend or diffract around surfaces. But what they can do is bounce off the ionosphere. So this is like a layer in the atmosphere. And this gets very, very charged up. So this is like the upper atmosphere. This is the ionosphere, and this gets charged up. And so radio waves can't really get through this interference because the particles are all charged. But what happens is the radio signals will bounce off the ionosphere like this. So you have the similar sort of range as you would with long waves, except they don't diffract into tunnels or around buildings. So, you know, shortwave radios you won't really hear in certain places, which may be obscured. Okay, so can you add that in, please, and just explain what's happening? So shortwave radios, okay, they don't diffract around surfaces, but they do bounce off the ionosphere. And we'll just actually add in ionosphere. You know actually what you're talking about. There it is. Okay, so that's just part of the atmosphere. Okay, so once again, pause the video and do that now, please. Okay, welcome back. So, as you might have spotted, we're unable to communicate all the way around the world because what we have is the curve of the Earth prevents that. You need to have line of sight. You need to be able to see where you're sending the signal. Now, obviously, radio waves can't do that because long waves can't bend around the Earth, and short waves eventually will be absorbed by the ionosphere or the atmosphere or the Earth. So, how do you send a signal? We can't use radio waves because they're long wave, low energy, and so they don't have enough energy to get through the interference in the ionosphere. So what we do is we use the next sort of waves up on the spectrum. We use microwaves. And microwaves have a much higher frequency and a shorter wavelength. That means they've got enough energy to punch through the ionosphere. But what we have to do is that line of sight rule still applies. So we use satellites. So if I want to send a signal like that, I can send it up to my satellite and then beam it back down to my receiver over here. But I cannot use radio wave for this. I have to use microwaves. Okay, next one up. So can everyone please just add to the diagram that we use microwaves to send signals. And the main reason for this is a higher frequency, which means they have enough energy to get through the ionosphere, and then we use a satellite to direct the signal because we still need to have line of sight. You still need to be able to see where you're sending this signal. Okay, so once again, pause the video and do that now, please. Okay, welcome back. So just to finish off, I'm going to put in assignments all the things that you should do, but essentially what diagrams that you need to copy into your book are on page 78 in your book. And also 77, just in case you missed the part about the practical. Okay. It also has a nice bit on refraction on page 76. So I'd recommend you go to your revision guide and use that today. So there are 3 diagrams that you'll need. I'll put that in assignments. And there is also a sheet which will take you about 5 minutes or so. So just a quick summary about how the different waves in the electromagnetic spectrum are used. So as always, I'll be online to help if you need any. Good luck.